Use your handout to make notes and fill in the gaps as you look through the slides in this video. Keep stopping the video and making sure you really understand it, and of course consult your textbook as well. Alkenes are hydrocarbons like alkanes. Alkenes, though, are unsaturated molecules. That means that they have a higher proportion of carbon in them than in an alkane, so they've got less than the maximum amount of hydrogen. If they've got a higher proportion of carbon in them, it means that when they burn, they produce smoky flames because the flames have actually got carbon in them, making the smoke. The physical properties we have to talk about are just the melting points and boiling points, which are lower than the corresponding melting point and boiling point of the corresponding alkane. This is because when you've got a double bond in a molecule, it's more difficult to pack the molecules close together. Therefore, the molecules can't get so close, and the melting point is easier to melt them. Here's a skeletal formula for an alkane with fairly regular angles. When there's a double bond in the molecule, then the angle changes where the double bond is, and consequently the chains have a bit of a kink in them, and that makes them more difficult to pack together. This is why saturated fats are solids, that is, fats that are coming from animals like butter and lard, whereas unsaturated fats tend to be liquid at room temperature, and we call them oils, so sunflower oil and vegetable oils. We are going to look at five reactions of alkenes, but the first four all fit into the same general pattern. You start off with a double bonded molecule and you end up with a single bonded molecule. You lose the double bond, the pi bond of the double bond, and you get two new covalent bonds joining to two new groups. So, as I said before, when AB reacts, you lose the pi bond. So, just drawing the sigma framework, we then, having lost that pi bond, are able to make two new bonds to the A and the B. A reaction like this, where a double bond is lost and turns into a single bond and two molecules join up together to make one molecule, is called an addition reaction, and at least the first three of these are definitely addition reactions of alkenes. When hydrogen reacts in an addition reaction with ethene, we end up with ethane. It's an addition reaction. We've lost the double bond and we have ended up with a molecule that has all single bonds. The product is ethane, C2H6, and the conditions for this reaction: you need a nickel catalyst at 150 degrees C. Alternatively, a platinum catalyst will enable this reaction to happen at room temperature. So this reaction is known as catalytic hydrogenation of an alkene, and it is used to turn vegetable oils, into solid fats by increasing the amount of saturation in the molecule, so removing the double bonds by putting hydrogen across them in an addition reaction. When halogens react with alkenes, the same type of reaction occurs, an addition reaction. And the product is 1,2-dibromoethane. The conditions for this reaction are simply that the ethene is bubbled into liquid bromine or bromine dissolved in an inert solvent such as carbon tetrachloride. Chlorine and iodine would react in exactly the same way in this addition reaction. The halogens are acting as electrophiles, so the Br is attracted to the negative charge in the pi bond, so this is called electrophilic attack. The bromine electrophile therefore bonds to an electron-rich site in the molecule, the pi bond, and it accepts a pair of electrons from that site to form a new covalent bond, which you can see just here, obviously. Last thing to say about this reaction is that if you are using bromine in its liquid form or in an inert solvent, or alternatively bromine dissolved in water, what happens is that the bromine colour is lost as the double bond reacts and you form 1,2-dibromomethane. So this is a useful way of testing for unsaturation in a molecule, because the bromine starts off a browny orange colour in the solution or as the liquid, and it is then decolorized, loses its colour as it reacts and the bromine gets used up. Can you now write what the product would be if you were reacting bromine with propene as a molecule rather than ethene? And of course name the product. The third addition reaction we are looking at of alkenes is the reaction between a hydrogen halide and the alkene. Again, just reacting in the same way, loss of the double bond, and the H and the Br bonded like that. Of course we can represent this in the form of an equation just like this. Putting state symbols in. The product is a colourless liquid and it is of course called bromoethane. The conditions for this reaction, you simply mix hydrogen bromide, which is a gas, with ethene as a gas, and it takes place at room temperature. If you now have a go at adding hydrogen bromide to a molecule of propene, you will see that there are two possible products, and we're going to explain that later. This is an electrophilic addition reaction. The electrophile in this molecule is the hydrogen end, because the molecule is polarised so that the hydrogen is delta plus and the bromine is delta minus. So the H bit is attacked by the electrons from this bond here. With the fourth reagent, potassium manganate 7, which you probably know better as potassium permanganate, a purple solution, what is produced? This time is an alcohol, but this molecule has two alcohol groups, so we call it a diol. We represent this by a bit of a cheating equation. So you can see here this O in square brackets. This is a much simplified equation of something that's more complicated going on. The reaction is an oxidation. Potassium manganate 7 is a good oxidizing agent, and it has oxidized the double bond to a molecule that has got two OH groups, so is a diol. Normally the conditions for this reaction are that you would shake the alkene with a cold dilute solution of potassium permanganate in dilute acid, and if that is the case, then the purple colour of the potassium manganate 7 disappears as it is reduced itself, the MnO4- ion has reduced itself to a pale pink manganese 2+ ion. The product's name is ethan 1,2-diol, and this reaction is useful in that that product has some uses, but also the decolorization of the purple potassium manganate 7 is another way of testing for unsaturation in the molecule. You should make a note of those observations then, that dilute acidified potassium permanganate is decolorized from purple to colourless if a double bonded alkene is shaken with it. If you vary the conditions to a neutral solution of potassium permanganate, that purple colour is lost but replaced by a brown precipitate of manganese 4 oxide, MnO2. So you do have to be careful about the conditions that you do your reactions in. As we've done before, will you now try to write the structural formula of the product of the reaction of propene being shaken with cold dilute acidified potassium manganate 7 solution. A further example of addition is shown by the polymerization of alkenes, but that you'll have to come across in the next video.